Je vais faire ma présentation en anglais parce que mon français c'est là. So the topic of today's presentation is can quantum mechanics improve radar technology? And a short answer is not really. And we will now see why is that. So let me start by stating which is the problem that we are interested in. So we want to detect a target that is embedded in a thermal background. And we want to compare two strategies to detect this target. The first one is we have a sender that sends a signal to the region where there may be or not be a target. We look at the light that comes back from this region, and we try to make a decision if the target was there or not. So in this case, the signal contains, let's say, m times n s photons, and we just measure the return light. A quantum strategy instead would consist in generating entangled signal-hydride pairs, each one with ns photons, and we generate m copies of this entangled state. We send the signal beam to the region where there may be the target, and we keep the idler. So one part of the entangled pair we keep in our lab, and we delay it until we get something back from the region where the target may be. Then we perform some quantum measurement on the retained idler and the return signal, and we try to exploit the correlations between the signal and the idler to detect the presence of the target. So these ideas are, in fact, quite old. So the first proposal of using entanglement to detect a target is from September 2008. It's this paper from Seth Lloyd in Science. But actually, this paper did not present a comparison between a classical radar and a quantum radar, but it presented two quantum strategies, one consisting in sending single photons to the target, and the other one sending entangled pairs to the target. And both strategies actually are not better than a classical radar. But fortunately, a few years later, there was the proposal of what is the actual quantum radar protocol, which is called Gaussian quantum illumination. And I will discuss these in details later. But when the protocol was proposed, it was only clear which was the ultimate limit that this protocol could reach, but it was not clear at all how one could experimentally reach these limits. And to obtain some proposal to how to actually measure the advantage that quantum illumination can provide, we had to wait the next year. And this was mostly restricted to the realm of optics. The first proposal in the microwave regime appeared in 2015. And the same year, there was also the first demonstration experiment, which was done in the optical domain. And only a couple of years ago, it was found which is the optimal measurement that one should do to saturate the ultimate quantum advantage that quantum illumination can provide. And in the last few years, there were also several experiments on quantum illumination in the microwave regime. But most of these experiments are not conclusive, so they cannot demonstrate the true advantage of a quantum radar. And the reason is that they usually show plots like this, where this is the probability of detection of a quantum radar. This is the one of a quantum radar, of a classical radar, sorry. And they say, okay, this is higher, so this is better. But the quantum radar they are considering is not the optimal one. And the classical radar is also not the optimal protocol that they could use. So they're just showing that one protocol is better than another one. But if they were using the optimal protocols that they could use with their setups, the classical one would actually perform better. So we cannot conclude from these experiments that a quantum advantage has been demonstrated in the microwave regime. So what I will focus on today is mostly the Gaussian quantum illumination protocol, so how really this works, and then I will say something about which are the receivers that one can use to saturate the performances of this protocol. So the framework that one used to characterize the performances of a classical and a quantum radar is the one of binary hypothesis testing. Riyad was mentioning the second quantum revolution, and a characteristic of the second quantum revolution is that one combines elements from quantum mechanics with elements of information theory, and hypothesis testing is typical from information theory and how to do hypothesis testing for distinguishing quantum states is quantum information theory. So we have two hypotheses that we want to probe. One is the target is not there, and the other one the target is there. And we can make correct decisions so that we say that the target is there when it actually is. Sorry, the target is not there when it is not, or that the target is there when it is actually there. So this is wrong here. It should be H1 when H1 is true. Sorry. And then we have two possible wrong decisions. One is that we say that the target is there when it's not, and this we call a false alarm error, which is associated with the false alarm probability. And then we have the opposite case when we say that the target is not there when it is actually there, and we call this a miss kind of error. So we missed our target, and it's associated with some miss probability. Now, if we consider classical probabilities, then we have two probability densities which are associated with the two hypotheses. And these probability densities will depend on some real variable which span a space which we call the decision space. And then we can divide this space into two regions. And the region Z0 is associated with the hypothesis 0 to be true, and the region Z1 is associated to the hypothesis 1 to be true. And then the false alarm probability is the integral of the probability density of the hypothesis 0 over the region where Z1 is true. And the miss probability is defined the other way around. Now, if you want to extend this concept to quantum mechanics, then we replace the probability densities with quantum states. So this is the density matrix rho 0, rho 1, which represents the two states, which would be the state of the light returning from the target region when the target is not there or when the target is there. And then this division of the decision space corresponds to identifying two measurements operator, and one which is associated with the hypothesis 0 and the one is associated with the hypothesis 1. The sum of these two operators gives the identity, which corresponds to say that the decision spaces spanned by the two hypotheses span the full space. And then we use the rules of quantum mechanics, and we define the false alarm probability as the trace of the measurement operator associated with the hypothesis 1 over the state associated with the hypothesis 0, and the miss probability is the other way around. And then we can have two decision strategies. First one is what is called a biased decision strategy. So we consider some a priori probabilities of the two hypotheses being true, and one minimize the mean error probability. And this is the strategy where first quantum illuminations has been studied. But then there is this other strategy which is more relevant for radar application, and it's this one fix a tolerable threshold of false alarm probability, so which says I can allow myself, I don't know, a 10 to the minus 4 probability of saying that my target is there when it's actually not, and then I minimize the probability of missing the target. Or in other words, I maximize my probability of detecting a target that is there when it is actually there. So for historical reason, I will start by discussing quantum illumination in this strategy, so in this setting, and then I will show what instead happens in this strategy, which is more relevant for practical applications. So let's go back to this picture here, and let's just introduce some more parameters. So we say that the target is represented by some weakly reflective object, so which has a reflectivity kappa, which is much smaller than 1. And it's embedded in a very bright background. So the number of photons in the background is much smaller than 1. And a classical strategy, quantum mechanically, corresponds to say that we send a coherent state with a mean photon number m times ns. A coherent state is the quantum state of light that more closely resembles a classical beam. And while here we consider a particular entangled state, which is called the two-mode squeeze vacuum. We will see a bit more details about this state later. And then, as I said before, one perform a measurements on the retained idler and the return signal. And here are the performances of these protocols for some different regimes. So the red line here is the performance of the quantum illumination protocol, and the blue line are the performances of the classical illumination protocol. And what is plotted here is the logarithmic of the mean error probability divided, against the number of copies of the states that we are using, also in logarithmic scale. And so here we see that the mean error probability is lower for the quantum protocol, so it means that we have a quantum advantage. However, one should notice that here we are considering beams which has a very, very low photon flux. So the number of photons in the signal, here it's much smaller than 1. If one instead, and in this regime, the probability of error for the classical case is approximated by this expression here, where here we have the number of copies of the state we are considering, the reflectivity of the target, the mean photon number in the signal, and here we have divided for the number of photons in the thermal background. And while in the quantum case we have the same thing, but we don't have these 4 in dividing the exponent, and so one often finds that quantum illumination provides a 6 dB quantum advantage. What one should correctly say, it provides a 6 dB improvement in the error probability exponent in the Bayesian setting. And the problem is that if we increase the number of photons in the signal beam, so here I just go to 1, we see that these two curves becomes much closer, and if one goes to a significantly high number of photons in the signal beam, then there is no more any difference between the classical and the quantum protocol. And the other issue is that, as I was mentioning before in the historical overview, that we know how to saturate the classical illumination bound, because we know that one has to transmit coherent state and then measure the return signal by doing an homodyne detection, while at the moment where these results were presented the first time, how to detect the light in the quantum illumination setting, so how to exploit this quantum advantage even in this regime, was unknown. So now let me go a bit more into the details to why the quantum advantage is only restricted to the small signal regimes and why it's so difficult to exploit this quantum advantage experimentally. And so I will try to tell you something about Gaussian quantum optics, which is the framework that one used to derive these results. So first of all, let me introduce the annihilation and creation operators for the hydra and the signal modes. And one could interpret these as the quantum analog of the electric field operators for the signal and the hydra modes. And they are called annihilation and creation operators because when we apply them to the photon number state, so this is a state with n photons in the mode kappa, which could be the signal or the idler, then the annihilation operator removes one photon, and the creation operator adds one photon. And combining these two, one could define the quadrature operators, which usually in optics are called Q and P, and in the microwaves, usually they're called I and Q, where Q is P, which is quite confusing if you don't know that, but that's what it is. And the standard measurements that one can do in quantum optics are photon counting. So one simply counts how many photons there are in its state. Or one can do homodyne detection, which corresponds to measuring the quadratures of the field. Or one could do heterodyne detection, which corresponds to measuring, let's say, the fields directly. But because we're doing these quantum mechanically, we have Heisenberg's uncertainty principle that tells us that we cannot measure the fields with the absolute precision, but we introduce some extra noise, which we don't have when we do the quadrature measurements because we have the same noise on A and A dagger, and so the noise cancels in this kind of measurements. Now, let's look at what we have in quantum illumination. So, in quantum illumination, we consider states of our field, which are Gaussian states, which one could interpret as these operators being the quantum analog of a complex Gaussian random variable. And since these are Gaussian, they are fully characterized by their mean and their second moments, so the variances. Now, we say that for the classical illumination protocol, we consider the coherent states. And these states are characterized by a mean field, which is square root of ns. So we have the mean of the field is given by the square root of the total number of photons. But if we look at the correlations, so that's the correlation between the variance in the signal, these are 0. And then we have a peculiar entangled states that we consider in the quantum illumination protocol. This is called the two modes with squeezed vacuum. And for these states, the fields mean both in the signal and the hydra are 0. And the mean intensity in the signal and the hydra beam is equal to the number of photons in the signals. So this is basically the photon number operators in the two modes. Now, what we have is we look at this kind of correlation between the signal and the hydras, there are none. But if we look at the correlation between AS and AI, we have these correlations which scales like ns times ns plus 1 square root. And so if we consider these as a correlation between fields, here we have this dagger, which is an Hermitian conjugate. So if we consider these as fields, this would correspond to a complex conjugate. So this is basically what these are called phase-insensitive correlations, because the phases cancels in the complex conjugation, while these kind of correlation are often known as phase-sensitive correlations, and these kind of correlations are hard to access. Another thing that we should say is that there are bounds on these correlations. So for classical correlation, this correlation cannot exceed this limit, while in the quantum case, this limit can be exceeded. This quantity is larger than this one. And for a fixed mean photon number in the state, then this is the maximum value you can achieve. So now let's have a direct look at what happens when we look at the modes that comes back from the target region. So the field in this mode is represented by the operator AR, which is the return mode. And when H0 is true, so that the target is not there, basically our field is replaced by the field of a thermal state, while when the target is there, we get a small portion of our signal field, which is reduced by this value kappa here, and then this field is mixed with the strong thermal background. And now, if we look at the phase-sensitive correlations in the output state, when this small portion of the signal is still there, then we get some residual correlation, which are strongly reduced by this kappa value here, while when we just get the thermal noise, in the thermal noise there are no it's not correlated with the idler that we kept in our lab, so these correlations are now 0. And if we instead look at which are the maximal classical correlation available in a field with the kappa and S photons, well, that's this one. So these correlations here are larger than this one, and this is where the quantum advantage comes from. However, one can see that if we increase an S to values significantly larger than 1, then these and these are basically the same, and that's why the quantum advantage goes away. So the take-home message of this more technical part is that the two hypotheses are distinguished by the phase-sensitive correlations, that this difference in phase-sensitive correlations disappear when the photon number in the signal increase, and that standard techniques like homodyne measurements or photon counting do not allow to measure these phase-sensitive correlations directly. So how can we exploit the advantage from quantum illumination? Well, the first proposal was to use an OPA, which is an optical parametric amplifier, or its microwave analog. And what this device does basically is to map phase-sensitive correlation into photon number. So we inject the return signal and the idler into this device, and then we count the photon on the amplified idler. In this way, we can measure the phase-sensitive correlations, but if we do these relatively simple measurements, this is something that optically can be very easily done with tabletop devices. In the microwave, it's a bit more tricky, but for example, Benjamin Huart, who will come next month, knows how to do that in his lab with microwaves. So it's a doable measurement in current experiment. And if we do this kind of measurements, the mean error probability is this one. So in the classical case, we had a 4 here. Here we have a 2, but the ultimate quantum limit is that when we don't have anything here. So between these and these, we had this 6 dB advantage, and between these and these, we only have a 3 dB advantage. And the difference is now plotted here. So we have the optimal quantum, the OPA receiver, which is this one, and the classical one. So we have a way in the lab to exploit the quantum advantage, which is achievable with current technology. But if we want to saturate this ultimate limit, we need to use something extremely more complicated, which is a device that combine all the M return signal mode and retain either by using some frequency generation. So some frequency generation is a process where you combine two photons at different frequencies into a single photon whose frequency is the sum of the two. And with this device, one needs to split the signal into several parts and then perform several nonlinear operations and condition the next nonlinear operation on the results of a previous measurement. So it's a very complicated iterative measurements, which is completely beyond what it can be currently done both optically and in the microwave regime. But in the limit of a large number of cycles of these iterative measurements, one can saturate the 6 dB limit of this of the quantum advantage. So now let me move to the quantum illumination with the Neyman-Pearson strategy. So in this kind of, when one uses this kind of strategy, what usually does is to plot the detection probability as a function of the false alarm probability. And so here we have in blue the classical illumination, which we said it's coherent states plus homodyne detection. And we can find the exact expressions for this curve. And when we use the OPA receiver, then the hypothesis testing that we had to do is to distinguish between two Gaussian signals with different variance and different means, but we can do that approximatively, and we obtain this green curve. And then with the optimal receiver, we have an approximation that we can use, and we see that the performances are much better, and it's what we see here in the red curve. Another way to present the same results is to introduce instead a different matrix, which we call the signal-to-noise ratio. So we can define the signal as the number of received photons. This is the number of sent photons multiplied by the reflectivity of the target, which reduces the number of received photons. And then we have this M, which is the number of copies of the state that we use. So this is the total signal that we receive back divided by the number of photons in the thermal background. So this is a naive definition of the signal-to-noise ratio in this case. And here we plot the probability of detection as a function of the signal-to-noise ratio for the classical illumination and quantum illumination. With quantum illumination, we mean the full performances, so the one that allowed for the 6 dB advantage in the Bayesian strategy for different levels of false alarm probability. And what we can notice here is that the classical strategy are much more spaced than the quantum one. And then we see that here there is a range of signal-to-noise ratios, let's say between, 0.01 and 10, where quantum illumination performs significantly better than the classical illumination, meaning that we can get the same probability of detection with a much lower signal-to-noise ratio. And what we can also see is that if we look at this kind of plot, the signal-to-noise ratio quantum advantage is not limited to 6 dB. So if, for example, we define the quantum advantage as the ratio between the signal-to-noise ratio in the classical strategy minus the signal-to-noise ratio in the quantum strategy to reach an 80% probability of detection, then we see that for different level of false alarm probabilities, then the quantum advantage, it's different and can be in principle, unbounded. Yes. So now the conclusion is that we found a regime where the quantum illumination provides a clear advantage, and the important question is now, is this regime where the quantum advantage clearly is there, is practically relevant? And to answer this question, let us have a look at how entangled photon pairs are produced. So here I have a sketch which reminds more of an optical process where we pump a nonlinear crystal with a beam at frequency omega p and with the wave vector kp, and then at the output we obtain pairs of photons at frequencies omega s and omega I, and with wave vector ks and ki. But the analog of this process can also be done at microwave frequencies, where instead of a nonlinear crystal, one uses a superconducting circuit. But the point is that to be able to do, for this process to occur, one needs both these conditions to be satisfied at the same time. So one needs that the sum of the frequencies of the emitted photons match the frequency of the pump, and also the sum of the wave vectors. So these two conditions are usually satisfied at the same time only for a small bandwidth, which is known as the phase matching bandwidth. And typical values of the phase matching bandwidth in optics for, say, a signal at 100 terahertz are of the order of 1 terahertz, while in the microwave, for signals around 10 gigahertz, current devices have phase matching bandwidths which are around 100 megahertz. And now, if you want to, let's say that we want to generate 1 million of copies of these entangled photon pairs, and since we want to stay in the region where we have the quantum advantage, we want these photon pairs to have a very low flux. So the two beam will have a mean photon number which is smaller than much smaller than 1. Let's say 10 to the minus 2 here. Now to have these many copies, we need a pulse which is long in time. The number of copies divided the phase matching bandwidth. And so for having these in the optical regime, one will get a pulse which is about 1 microsecond, while to have these in the microwave regime, one will get a pulse which is 10 milliseconds. And this is already a problem, because this pulse is too long to probe a moving target which is very far away. And moreover, if we look at the power that this pulse would contain, this power is only a fraction of a femtowatt, so 0.1 femtowatt. So to have 10 to the 6 copies of our state, we get this very, very little power at the sender. So the power that we will get back will be even lower. And how lower could be, I don't know, 10 to the minus 10 or 10 to the minus 20 lower in typical long-range radar application. While the powers are acceptable in the optical regime, and also the pulse length is acceptable in the optical regime, but in the optical regime there is no thermal background, or the thermal background is so low, then the signal-to-noise ratio is then very low, and we are in a regime, very high, so we are in a regime where there is no advantage in using quantum illumination. So the regime where these would be useful would be the regime of strong thermal background that we have for the microwaves, but we get pulse lengths which are completely incompatible with the typical radar application and powers which are extremely too low. And this is kind of more of a practical problem, but it's a practical problem that there is no way to overcome, because this phase matching bandwidth could increase, but it could not increase of, I don't know, 10 or 20 order of magnitudes, which is what one would need to get significant powers in the regime where one has a quantum advantage. And on top of that, there are other problems. So these are the two problems that we just discussed, so that we cannot increase the power by increasing the number of photons, because otherwise we lose the quantum advantage. And the time bandwidth product, so that the bandwidth is limited, and so the time length of the pulse is limited by the fact that in quantum illumination one needs to probe exactly one point in space and, in a sense, in time, because you need your signal to come back from the target region and to be perfectly matched with the idler that you are keeping in a delay line in your lab. And another problem is that how you do the delay line in your lab. So you need what is called a quantum memory, where you store your idler in your lab for the whole round trip of the signal to the target and back. And if you have losses in your quantum memory, this would also reduce your probability of detection, because then you get a mismatch between your signal and idler. And also in a classical radar, you can send multiple spatial frequencies at the same time to probe different points in space at the same time, and then rematch them with in post-processing with what you're keeping in your lab. And this you could not do in a quantum experiment, because you always need to recombine your return signal with the retained idler on some quantum devices to detect the phase-sensitive correlations. So this means that with a quantum illumination protocol, you could only probe really one single point in space at a time. So these are the reasons why the practical use of quantum illumination for target detection, especially for long-range target detection, is probably very, very limited. And thank you for your attention. If you want to have more information about these, we wrote a technical report, and which is also on the archive. And next week, probably, or a few weeks, we have a new version of these on the archive, which is hopefully the final one. Thank you.